back to another video in our lecture wrap-up series here for Engineering 17, Section 2 in the spring quarter 2014 here at UC Davis. So today was lecture number 5. The main topic of discussion was two primary things. Number one, using mesh current analysis and kind of looking at also how that compares to our node voltage analysis that was covered in the previous lecture. And then also getting into another tool we can use for simplifying circuits by using source transformations, converting a voltage source in series with a resistor into a current source in parallel with the same resistor value, and how we would go about doing that. So to just give a quick, again, overview, wrap up of the mesh analysis, I have another example circuit for us to look at here and to go through this analysis. In the special case that I've put into this one, which we didn't get to in class specifically, was when we have a current source, which in this case will really help simplify things quite a bit. So again, first thing in doing our mesh current analysis is to define the mesh currents. Again, you should immediately recognize that we have three meshes here, so we're going to define a given current for each one of these. So let's say this is I1, this one I2, this one I3. And again, the direction of which you define those currents looping in each of these loops, doesn't really matter. Typically, I just write them all clockwise, and that's what most people like to do. But it would make no difference if I made those counterclockwise, as long as I follow the right conventions when I start going around each loop and defining using the KVL method. But in terms of our mesh currents, as long as we're consistent in the positive and negatives of each of the given currents, that'll be fine. So again, let's start here in loop I1. Let's say mesh 1. All right. So mesh 1, let's say starting here, first thing I got a voltage drop across the 3 ohm resistor here, and the only mesh current that's affecting that is I1. So it's going to be I1 times my 3 ohm resistor there. So let's say it's 3I1. Then coming down through this, the voltage drop across the 2 ohm resistor here is going to be dependent not only on my mesh current I1, but also what's opposing that with my mesh current I2. So for that one, I'm going to say that's going to be the value of the resistor times I1 minus that opposing current I2. All right, and coming over here, we have a 6 ohm resistor. So again, a voltage drop across here defined as 6 ohms times the I1 mesh current, the only one that affects that there. And then here I have a voltage rise of 30 volts from this source right over here. So that is going to count as a negative minus 30 equals 0 there. So that's our equation for first mesh. So we could write a similar equation for mesh 2. In that one, let's start over here. First have a voltage drop across our 8 ohm resistor. So it's going to be 8 by I2. Plus going down to this 5 ohm resistor, again a voltage drop of the difference between I2 and I3. So 5 by I2 minus I3. 4 ohm resistor here at the bottom, only affected by I2. So we're going to add that 4 by I2. I'll continue this equation down here. The last one is a 2 ohm resistor, which again has I2, but it now being counteracted by the I1 mesh current. So it's going to be, let's see, we'll go over here, plus 2 by I2 minus I1. That all equal to 0. All right, so that's our KVL equation using mesh currents for this mesh 2. And then in mesh 3, so really we don't have to go through the whole process here because we don't specifically know what the voltage drop is across this current source per se. That would kind of be correlated to what the voltage drop is across the 5 ohm resistor, but rather than writing that whole equation and inserting another variable like we kind of gone through in the example of class, we simply know that I3 in this case, what this mesh is telling us is simply that I3 is equal to minus 16 amps. Again, that's because of the fact that this current source here is facing in the upward direction, whereas my mesh current, as I've defined it, is traveling in the opposite direction. Therefore, that's going to be a minus 16, which is the value of that current source. Now, then with the fact that I know what my mesh current I3, the value of that is, I can plug that back into this equation here to simplify. Then I would wind up with only two equations, two unknowns, and I could solve those systematically to evaluate the entire circuit. Okay, so moving on real quick, we also talked about source transformations, and I'd like to cover that. Just hit on one additional point that I didn't quite get to in lecture, but again, so keep in mind, for source transformations, what this allows me to do is if I have a voltage source in series with the given resistor R, I'm able to transform this back and forth with a current source, same polarity, in parallel with a resistor of the same value R. And we went through the process of explaining why this is, and we also explained the process of why IS is equal to VS over R if I'm transforming from this into this. Vice versa, if I had a current source in parallel with the resistor R and I wanted to get it into a voltage source in series with the resistor R, that would be my VS would simply be IS times R. Now, one other thing that I didn't quite get to that's in the lecture slides was if you come across something such as this, where maybe I do have my resistor in series with a node, but maybe I have another resistor in parallel with my source here. How does that change things? Well, so for all intents and purposes, and thinking about specifically what's happening at these nodes here, I can actually transform this in the exact same way as I'm doing with this version here, and so almost sort of negating the impact of this. And that's simply because, as I know, because this resistor is in parallel with this voltage source here, the voltage potential across that is the same, and therefore I can still do this transformation and simply go from what you see here directly into what you see over here. And similarly, if I had a current source that had that parallel resistor in it, but maybe also had a resistor in series, I could still do the same transformation again, despite the fact that I have this extra resistor sitting in there. There's actually ends up being no net impact at my terminals, which is really what I need to be sure I'm equating to. So again, if I had this situation, even with that extra resistor here, I could still transform this into this configuration using the same method. Don't need to add anything extra with this resistor value. Again, because in this case, the current going through that resistor, the current is the same going through this part of the branch as it is going through this part of the branch, so it doesn't affect, again, the net current that's being outputted to whatever my load is at the end of these terminals. So that was the last bit that I didn't quite get to cover. There's more details on this in your book if you like further explanation. And that about wraps it up for Lecture 5. Hope to see you on Thursday. Stay classy.